Hello, happy physics people. I wanted to walk through how we would solve a circuit like this practice number 2 using a VIR chart. Remember VIR, voltage, current, and resistance, and this is a helpful way to think about our circuits because with Ohm's law, remember we have this relationship V equals IR, and so this chart, everything should line up so that this column is equal to the current multiplied by the resistance in these two columns. All right, this is also a helpful way to organize our information. If we start looking at the circuit that we have here, we have 3 resistors, and so I've written 1, 2, and 3, and I've numbered our resistors. We can start off by kind of filling in what we know. Resistor 1 has a resistance of 2 ohms, and so I'm going to fill in a 2 right here. Resistor 2 has a resistance of 3 ohms. Resistor 3 has a resistance of 10 ohms, and we know that the current flowing through that branch of our circuit is 4 amps, so I can put a 4 here in our current column. The last 2 rows that I have on this chart are labeled total, and that refers to the total of what's going on in our circuit. So it means the total voltage that's being supplied by our battery, as well as the total current that would be passing through the battery before it splits off at these junctions. The resistance column on that total row is going to refer to the total equivalent resistance of all 3 of those resistors combined in series and parallel in that relatively complicated configuration. This row that I have here, labeled 1 and 2, is referring to the combination of resistors 1 and 2. They're in series here along this parallel branch, and so when I think about them, it's going to be helpful, and you'll see this in just a second, to think about them together at some points, and so you can add rows as you need them onto your VIR chart. All right, looking at the information that we have, I think it's always easiest to start with where you know the most information. So that's about this branch where we have resistor 3. We already know the current and the resistance, which means we can just multiply 4 times 40 IR to find our voltage, and that's going to give us a total voltage of 40 as we pass over this resistor. All right, when we look at this loop, the loop where that resistor is located, and we think about Kirchhoff's loop rule, if we're going to lose 40 volts as we go through that resistor, that means that we are also gaining 40 volts when we go through this battery. So where I have the total, that total is also going to be 40 volts because on this loop, we lose the total voltage as we pass through that one resistor. All right, the next step as I'm filling this in is am going to look at my other 2 resistors. Now they're in a series combination on this branch, one right after the other, which means the equivalent resistance, if we're looking at something in series, is just the sum of those 2 resistances. So in this row labeled 1 and 2, I can fill in that the total resistance here is going to be 5, because 2 plus 3 is 5. All right, the other thing I know about that row is that it's part of this smaller loop. So if I look at the smaller loop and I consider that in terms of Kirchhoff's loop rule, we just said that the voltage on this battery is 40 volts. Okay, so that means I gain 40 volts when I go through the battery from negative to positive. And then as I go through resistors 1 and 2, I'm going to lose all 40 of those volts before I come back to where I started. Now, it's tempting to say, okay, well, if I'm losing 40 volts, there's 2 resistors, I would lose 20 volts over each one. But if you look at this, they don't have the same resistance, so that's not going to be a good assumption. They're not going to lose exactly the same amount of voltage over each one, simply because their resistances are not the same. But if we think about them as a combination, as 1 and 2 together, we know over both of them together, the voltage there that we're going to lose is still 40 volts. All right, now we have this this row, where we know 40 is equal to the current multiplied by 5, where that's our resistance. So we can divide. 40 divided by 5 is going to give me 8, and that tells me that the current through here is 8 amps. Okay, now, if we think about how current behaves in a circuit, if the current goes through one of these resistors, it's going to go through the other resistor, and so the current through resistor 1 and resistor 2 is going to be 8 for both of those, since they are both on that same branch of the circuit. All right, now I can look at resistors 1 and 2 individually, and I can say, well, the voltage is going to be the current multiplied by the resistance. 8 times 2 is 16. For resistor 2, the same thing. The voltage is going to be the current multiplied by the resistance. 8 times 3 is 24. And then if we want to just double check that those numbers make sense and we didn't do our multiplication wrong or have an error somewhere else, we can say, well, if we're going to gain 40 volts going through this battery, we'd better lose 40 volts across these resistors. And 16 plus 24 is 40, so that is still working out. The other thing to notice is that when we had a bigger resistance, resistor 2 has a resistance of 3, we are going to lose more voltage. And that makes sense as well. It's harder to get through that resistor. It has a higher resistance, and so it's going to take a little bit more energy out of those electrons as they're flying through our circuit. All right, we've got one row left, and that is our total row. When we look at this, the next box that I think is probably easiest to fill in is the current box, and that is because we already know these other two currents. If we look at what's going on in our circuit, we have this loop over here, and we have a 4 amp current going this way. Okay, it came right from down here. We knew that from the beginning. And we just found out that this current on this branch is going to be 8 amps. Well, if you think about Kirchhoff's junction rule, what that tells us is that the current coming into a junction has to be the same as the current going out of the junction. And in that case, that's going to be our total current. So we have 4 and 8 together coming in. That sounds like 12 to me, which means our current going out also has to be 12. So I can fill in here that the total current that's going to pass through here and then through our battery is going to be 12. All right, now we know that the total row here, our total change in voltage is 40, our total current is 12, and so if we wanted to know the total equivalent resistance of our battery, we could say, well, 40 equals 12 times the resistance. And then to find the resistance, we would just do 40 divided by 12, and that's going to give you 3 1/3, or 3.3. And now we know all the values for our circuit. So hopefully that's been helpful. Stay tuned and we'll look at practice 3 in a little bit.